This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over the ideal gas. So first, we'll just talk about ideal gases as a concept, and then we'll go over the ideal gas laws. Before we talk about what an ideal gas is, we need to establish what pressure is when talking about a gas. So look at this cube that we have below, and this cube is filled with a bunch of gas particles. These gas particles are moving around randomly, and they're colliding with the edges of this cube. And whenever they collide, they're going to be exerting a force wherever they collide. And keep in mind that there's actually millions, if not billions, of these molecules. So at any given point, or any given area in this cube, there's tons and tons and tons of these gas particles hitting it and exerting their force on that surface. So collectively, we end up with a pressure from all of those forces, and pressure is equal to force divided by area. So you would take the collective force, divide it by the area that they're hitting, and then that would give you the pressure inside of this cube. So pressure is the result of the collective collisions of the gas particles with their surroundings. The volume of a gas is measuring the space that the gas particles are moving in. So a solid or a liquid, the volume of those two is actually measuring the volume that the molecules themselves are taking up. But for a gas, we're measuring the space that the gas molecules are taking up due to their motion. So if you imagine this cube, for instance, or maybe a balloon or the room that you're in, there are gas particles bouncing around everywhere, but the particles themselves are taking up very, very little volume, but their motion is taking up a very large volume. Now we can talk about the ideal gas law. And the ideal gas law is a way of thinking about gases that is simplified. And we make a couple assumptions in order to simplify the gas. And the reasons that we do this is because it just gives us an easier equation to work with when we're trying to figure out different characteristics of a gas. So now we'll talk about those two assumptions and why they make this equation easier to deal with. The first assumption we make is exactly what we were just talking about, and that is that we assume the gas particles take up zero volume. And this makes it much easier because now the only volume we worry about is how much space the motion of the particles is taking up. If we try to also consider how much volume the particles themselves are taking up, things would get way more complicated. The next one we assume is that there are no intermolecular interactions between gas particles. And if we look at this cube below, we can talk about why we make this assumption. So if you pick any two of these molecules, pick two that are nearby, let's say this one and this one. If those two had intermolecular interactions, then what would happen would be their motion would be disrupted. And if their motion is disrupted, then whenever they collide with the walls, it's going to affect how much force they're exerting on the walls. So let's say with these two particles moving in opposite directions, if they were attracted to each other, it might slow them down. And then that would affect the pressure that they're exerting on the walls. So we just assume that whatever pressure is being exerted is due to molecules that are moving without any disruptions. And again, if we tried to include the intermolecular interactions, then our equation would get way, way more complicated. These assumptions do make everything a little bit easier, but they also can lead to slightly different results than maybe what reality actually is. For the MCAT, you really don't need to worry about that at all. But what you do want to know is how can we make conditions that are conducive to making a gas mimic an ideal gas? And the first thing we want to do is make a high temperature. The reason a high temperature helps a gas mimic an ideal gas has to do with those intermolecular interactions. So here is a gas molecule moving down, and then here's a gas molecule moving up. So if those two are moving very slowly, then there's a lot of time for those intermolecular interactions to form. But if they're moving extremely quickly, then there's no time for the intermolecular interactions to occur, and they'll just zoom right past each other. So having a high temperature helps to mimic the idea that there are no intermolecular interactions. The next condition we want to mimic an ideal gas is to have a low pressure. And remember we said that pressure is the result of all of the collective forces of the collisions between gas molecules and the surroundings. And it gave us this equation on the right. And one way that we can limit the amount of collisions is to have a very, very large container relative to the amount of gas particles that we have. And what that gives us is it gives us a very large volume that the gas particles are moving in, and then the volume that the gas particles themselves are taking up is very, very small relative to the total volume that they're moving in, and that helps to mimic a negligible volume of those gas particles. So that mimics the first one that we went over. Now we can look at the actual ideal gas law. And the equation is PV equals nRT. And we have it written over here on the left. P is pressure, V is volume, N is the number of moles of the gas, R is a gas constant that they're almost always going to give you on the test, and then T is temperature in Kelvin. So in the equation, you have 4 variables, P, V, N, and T, because R is always constant. So only 4 of those are variables. Most of your problems, they're going to keep 2 of the variables constant and then change one of the remaining 2 variables. And then based on the change of that variable, you need to be able to predict or use these equations to figure out how that affects the other variable that can change. So we're going to look at a few examples here to illustrate how to think through that. Our first example is this PV equals a constant. So that means that if the right side of the equation is constant, that N and T are constant. So N and T are not changing, but P and V can change. So mathematically, you could think about this as if P goes up, then what does V have to do to maintain a constant value on the right? And hopefully you can figure out that P would have to go down to counteract what P does. And the same would be true if V went up, then P would have to go down to counteract what V has done. Conceptually, you do want to be able to make sense of this as well. And imagine we have this cube here, just like we were doing earlier in the video. And if we increase the volume of this cube, so V has gone up, ask yourself what happens to P. And remember, P was the collective collisions of the gas particles with the surroundings. And hopefully you can see that as the volume goes up, we're going to have less and less collisions, which would make the pressure go down, which is exactly what we predicted. And then conversely, if volume were to go way down and get smaller and smaller and smaller, you can see that the amount of collisions would increase, thus the pressure would also increase. So that gives us this equation on the right of P1V1 equals P2V2. And what that's basically saying is that before we have any changes, so that's P1V1, what P times V equals must be equal to what P times V equals after those changes happen. And that's because P times V is equal to a constant before and after the change. So then PV1 must also equal PV2. For this next one, we're dealing with variables that are on opposite sides of the equation. So to conceptually understand this, I would first rearrange your equation to have V and T on the same side, which gives you V over T equals NR over P. And we're saying that V and T are the variables that can change, while N and R cannot change. So that means that the right side of the equation is a constant. So now think about if we change one of our variables of V or T, how does the other one change in order to compensate for that to keep what they equal constant? So let's say that V goes up. So if V goes up, then that means that what they equal is also going to go up. And in order to compensate for that, T needs to go up so that we're dividing V by a larger number. And then vice versa, if V or T were to go down, then the other one would also have to go down. So what we're really trying to do is just keep that ratio constant. And then on the right side, this is just illustrating what we said about how we want to keep the ratios constant. V over T needs to equal the same thing regardless of the changes that we make. So V1 over T1 are the initial conditions, and then V2 over T2 are the conditions after we've made our change, and they do need to equal the same constant each time. So you can set up your equation, V over T1 equals V over T2. The last one we'll look at is also looking at variables that are on different sides of the equation. So start by doing the same thing. We have V over N equals RT over P. And the thought process on this one is the exact same as before. We need V over N to always equal a constant. So if V goes up, we need to divide it by a larger number to keep that constant. So then N would go up. Same thing if V were to go down, then N needs to go down to compensate for that. And then on the right side, following the exact same logic, we end up with V over N1 equals V over N2. And just keep in mind, you can do this with any 2 variables you select. So anytime you're given a problem that you think an ideal gas law is about to be applied, just highlight what 2 variables are not changing, and then highlight what 2 variables are changing, and then go through this thought process. And what you should end up with is if the variables that are changing are on opposite sides of the equation, then you end up with one of these ratios that we have. And then if you end up with the two variables that are changing are on the same side of the equation, then you should end up with that first one where you have them multiplied together.